Okay, so it's my pleasure to open the afternoon session and to introduce Mikołaj Frączyk. Mikołaj Frączyk is a professor at Jagiellonian University. His research interests include locally symmetric spaces, measured group theory, homogeneous dynamics, and analytic number theory. He has published in very top mathematical journals, in particular Annals of Mathematics, American Journal of Mathematics, and Invenciones. He obtained his PhD at Paris Sud in 2017, and later on, for the next 6 years, he was on a prestigious postdoc position, first in Budapest, but in an ERC ground, then at the Institute of Advanced Studies in Princeton, and finally he was the Dixon instructor in Chicago. Since September 2023, he is a director of Dioscuri Excellence Center at the Jagiellonian University, funded by National Science Center with cooperation with Max Planck Society. And this is a program for 5 years with budget 1.5 million euro. So this is an enormous distinction. And last year, 2024, he was awarded 2 prestigious mathematical prizes in Poland, namely the Banach Prize of Polish Mathematical Society and the Prize of Ministry of Science, both for outstanding mathematical achievements. Mikołaj, the Zoom is yours, please.
Thank you. First question is that can you hear me? Because
yes,
we can
hear.
Okay, for a moment I was worried that something was slowed down. Okay, so if there are any problems or you cannot hear me, please let me know. So yeah, my talk will be just an introduction to an emerging area on the border of probability and geometry and topology. So everything is rather fresh, but you can trace back the ideas to kind of ancient times like the 60s or 50s. So let me, maybe first I'll do some shameless advertising. So in Kraków, we have this Dioscuri Center, and typically each year we have postdoc calls and PhD calls. So if you're looking for a PhD position or scholarship, you can take a look at our website, and every now and then there are announcements about new positions. Okay, so let me start by telling you the plan. So first I'll talk about probabilistic methods. Then I'll explain some questions in geometry and topology, which will focus on locally symmetric spaces. There are specific kinds of Riemann manifolds with very nice properties. And we'll finish with one example of how to use probabilistic method in that context of geometry and topology of locally symmetric spaces. Right. So let's start with the probabilistic method. So very broadly, how does it work? So suppose you're looking for an object with a nice property. I don't know, manifold that has some properties, or a graph that has some nice properties, but it's very difficult to kind of come up with an explicit example and verify that it has this property. So what you can do then, if you expect this property is actually not super rare, it's just annoying to verify, you could then try to come up with a random model that will produce some random object of the type you're looking for, and set the model in such a way that you can actually show that with good probability, positive probability, this object will have the desired property, right? And surprisingly, again, this maybe at first glance it looks like we just made our lives more difficult because we are looking at some models, but sometimes it's easier to prove using some tricks in probability, easier to prove that probability of an event is positive rather than find this positive instance, this actual instance of the event. Okay, so let me give you, we'll start with a simple example, which could be, I don't know, an exam problem or a competition problem. So we have 10 points in the real plane. And we ask, can we find an open cover by disjoint open disks that will cover all of those points, right? So you see, I have 10 points. You probably don't see my cursor, but oh yeah, you have 10 points, and we would like to cover all of them by disjoint open disks of radius 1. And this problem is actually sensitive to the number of points. So when number of points is very small, it's kind of very easy to show that you can do this by hand. But when number of points get very big, so for example, imagine that they sparsely fill the space, like a very dense grid, then it's also pretty clear that you actually cannot cover them by disjoint disks because the geometry of the disk will force the cover to have gaps. And if our collection of points is kind of dense enough, some of them are bound to fall into those gaps. So this is not entirely obvious problem, right? And it's also because the space of there are many ways of putting 10 points in R2. It's like 20-dimensional space of configurations. It's kind of difficult to imagine an algorithm that would kind of select the disks for you, and you can anticipate that such proof will be very painful. Okay, so what can we do? We can make some observations. For example, we can observe that it would make sense for the disks to be packed quite tightly because then the gaps are small and we kind of don't want big gaps because we want to cover everything. So let's try to cover this collection of 10 points by the densest circle packing that we know on a plane, actually the densest one, which is the hexagonal circle packing. So this picture here is not the hexagonal circle packing, is just some instance of a cover by disks that works, right? So yeah, so if we try to do this for hexagonal circle packing, this is the hexagonal circle packing. You see that it has gaps, so if we're not careful, some of those points might fall into those gaps. Yeah, but let's now, maybe I'll give you more details on this packing. So to get this hexagonal circle packing, you take the open unit disk, which is the one that has the starting point of those two vectors in the picture. And you translate it by all integer combinations of those two vectors. So those two vectors span something called hexagonal lattice in R2, and the translates of our disks by those vectors are provided disjoint, and they form the densest circle packing in R2. And this is kind of the same type of packing you see in grocery store when you see oranges, right? Right. So what we want to do is to try to kind of shift this circle packing in such a way that it will cover our 10 points. Okay. Is it possible? So we don't know that, but let's try to compute the probability that a single point on the plane is covered by this random translate of the circle packing. So maybe without going into too much details, this packing is periodic by this triangular lattice, the hexagonal lattice. So to get this random shift, you only need to shift by vectors which are in the fundamental domain of the lattice. So in this parallelogram that I've written here. So this parallelogram is parameterized as all combinations of V1 and V2, where the weights are between 0 and 1. And if you shift your original lattice by all those all those vectors, you actually explore all possible shifts because of periodicity. So the random shift will be just given by a translate of this original circle packing by a random element of this parallelogram. And if you want to compute whether any point is covered by the circle packing, you just need to compare the area inside this parallelogram, which is covered by the disks, versus the part that is not covered. And it turns out that the part that is covered covers approximately 0.9069 proportion of the area. So 90.6% of the you have 90.6% chance that random cover will cover your point. And this works for any point on R2. Okay, so this is kind of a simple computation. And now let's go back to our original problem. So we have our collection of 10 points. And because for each of those points, we know what's the probability that it will be covered, we can compute the expected number of points covered. And this will be just a sum of the probabilities that each point is covered. So as the formula written here, we sum up the probabilities that each point is covered. There are 10 points, so we have 10 times 0.9069, which is 9.06 something, which is strictly bigger than 9. So the expected number of points covered by random shift of our circle packing is actually bigger than 9. So what does this mean? So this means that, in particular, there have to be some instances where we cover more than 9 points, because otherwise we would see that the expected value is less than 9, right? Or less or equal to 9. So because of that, in particular, we proved that the probability that more than 9 points are covered is positive. But because we have only 10 points, the only option is that all of them are covered, right? So we just proved that there exists some shift, some translate of our circle packing that covers all of them. Well, this is very nice. We found our desired cover. Now we could discard the disks that are not used. We don't have to, but we can. And we solved our problem, right? And the solution is not so long, and it's definitely, at least as I imagine, simpler and shorter than any kind of attempt to explicitly describe the cover, right? We can ask about optimality. Will it work for 11 points? No. I don't know what's the answer for 11 points, but for 10, it's just enough. Okay, and
I have a question.
Yeah.
Just a quick question. So what is random here? These T1 and T2, these coordinates of these vectors, yes?
T1 and T2. So you're shifting your original, okay, this is the circle packing, and you're shifting it by random vector, which is of the form T1 times V1 plus T2 times V2, where T1 and T2 are uniform random elements of 0, 1.
Okay, so in order to define this expected value, what is random are those T1 and T2, yes?
Yeah, exactly.
Okay.
The cover is random there, and more specifically, as you say, T1 and T2 are random. Thank you. Yeah. So a few comments about this proof. So we have found the right random model, and we got our cover. We still don't know any explicit example for any given 10 points, but it's not hopeless, because when we apply this method, we can try several times, and by the law of large numbers, eventually we're bound to find the working shift. So it's not constructive, but probabilistically it works. And in this particular case, you would expect to find the right cover in 14 trials. And actually, the probability that you won't find it in n trials decreases exponentially fast in n. So this is pretty good for practical applications. And it's often the case that probabilistic proofs actually give you a probabilistic algorithm to construct the thing you were looking for. Okay. So this was like a exam problem level application. There are kind of more interesting applications, more difficult applications. And one that I like is about expander families. So those are certain graphs with special, very nice properties. And I think if you've never heard about this concept, then it's one of the, it's quite nice. So if you don't take anything else from this talk, just remember expander graph. So let G be a finite undirected graph. And for any subset of vertices, we define its boundary, denoted partial A, as the set of edges that connect A to its complement, right? So it's the edges that are kind of leaving A. And we say that the graph G is an H expander, where H is some positive constant, when for every small subset of the vertices, so in precisely less than half of all vertices, has large boundary. So the size of the boundary of the set is at least a constant times the size of the set. So this is sometimes called edge expander. There you can also define vertex expander, where you just define the boundary as not the set of edges leaving the set, but set of vertices adjacent to the set, but not in it. And this inequality about the size of the boundary being at least linear in the side of the set is called isoperimetric inequality. And a family of graphs is an expander family if all of them satisfy this inequality with the same constant, same positive constant. So you have a family of graphs, and you have uniform linear isoperimetric inequality. And if you are interested in maybe Riemannian geometry, you might have heard about isoperimetric inequalities. For example, in Rn, you would compare the volume of a set to the area of its boundary. So this is a related concept, but in graph theory. Okay, so let me give you some examples of first example of an expander graph. So expander graph expansion tells us about like how easy it is to get from one part of the graph to the other in some sense. So the most expanding graph is the complete graph on n vertices, and this happens to be an n over 2 expander, and this is the best constant you can have for a graph on n vertices. But this example is quite boring. Maybe I'll make a digression about kind of practical motivations for expander graphs. So expander graphs are modeling robustly connected networks. So those are networks which are very hard to disconnect, in a sense that if you want to disconnect a large chunk of the network from the remainder, you have to cut a lot of edges. Like number of edges should be proportional to the size of the chunk you want to isolate. So the network is very robust. If it's kind of, imagine that this is a physical network, and suddenly random subset of edges breaks, then in an expander network, this should still not be a problem. You should still be connected. Maybe there will be some small parts of the network that get disconnected, but they will be very small. So for kind of those practical purposes, you want those expanders, you want to have robustly connected networks, but you don't also want to use too many edges because they can be in some sense expensive. So we would like to find expanders that use less edges. The least amount of edges you need to connect the graph is already linear in the number of vertices. So you can ask, okay, can we kind of get this optimum number? So can we get, for example, expanders, expander families where the number of edges is just some at most a constant times number of vertices, or even you can make our life harder and ask for deregular expander families. And those are much harder to find. You won't have any obvious construction of those. I think when people define expanders, well, we'll talk about this later, but yeah, it's not obvious. So let me give you some non-examples of what doesn't work. So for example, this graph on the left, you see there are some two big chunks and one single bridge. So of course, cutting the single bridge would leave us with two big chunks. So this is not an expander. And also, if you look at a grid and some n by n grid, this grid also is not a good expander because you can make a vertical cut. The number of edges you need to cut is kind of linear in the length of the edge of the okay, if this is n by n grid, then this size of the cut is roughly n. But you have cut out two pieces that are quadratic in n. So compared to the size of the cut, compared to the sizes of chunks that you get, is quite small. So this is also not an expander. And it's any kind of construction that you can actually do in real life. It's big enough, it won't be an expander because, you know, you can, for example, if you take a cube, same problem happens. You can cut by hyperplane, and this cut is relatively cheap compared to the sizes of pieces that you get. So are there any bounded degree expanders? And it turns out that the answer is yes. And the first examples were found like this. So you take a uniform random irregular graph on n vertices. So the set of such graphs is finite up to graph isomorphism. And we just take a random one amount of them. And there are some kind of models, probabilistic models that produce those graphs. So you can work with them. And you can actually show that as n gets bigger, and I think you need d at least 3, then this random graph will be an expander with some positive constant. And this constant h, I think you can make it linear in d. And yeah, so by taking random graphs, you'll be getting expanders.
Excuse me,
And
what
actually,
is regular? Somehow I have missed.
the regular graph is a graph where all degrees are equal to d. So every vertex is connected to exactly d. Okay, has exactly d outgoing edges. If we allow loops or multiple edges, it doesn't mean that it's connected to the other vertices, but if we forbid them, then it would mean that it has exactly d neighbors. Any questions?
Are those graphs connected to Ramanujan graphs, or are those graphs?
Sorry,
Ramanujan graphs? Oh, maybe now.
Ramanujan graphs are the best expanders, so they are expanders. Yes.
Thank you.
So, but there are two ways of talking about expansion. One is like this kind of isoperimeter inequalities, and the other is spectral expansion. And Ramanujan graphs are the best spectral expanders. Yeah, and if you're asking whether those graphs are Ramanujan random graphs, I think this is like, if it's known, it's very, very recent. And maybe people believe that they are. Random graphs are almost the best expanders we can find. Right. So like just few words about the idea of the proof. So and this is to prove that it's not super hard. It's like it would take one lecture, but it's not like a super long proof. So for any subset of vertices, which is less than half of all vertices, you compute the probability that it has small boundary, which would kind of defeat the expansion. And you can show that those probabilities are very small as n gets big, and actually they sum up to something less than 1. So by the union bound, like if you have family events whose probabilities sum up to something less than 1, you have positive probability that none of them happens. But if none of them happens, then the graph is an expander and you win. So this is kind of, it's a very simple method, union bound, but it works surprisingly often. Yeah. And that's how people found first irregular graphs. And after that, there were many more constructions, sorry, the irregular expander graphs. After that, there were many more constructions with explicit examples. Okay. So there are many more applications of probabilistic method in combinatorics. But now I would like to move to the second part of the talk, which is about geometry and topology. And we'll quickly restrict to the setting of locally symmetric spaces. Those are spaces that I like the most. Of course, you know, there are many more questions you can ask about geometry and topology. But this is what I like. So those are Riemannian manifolds that are kind of very homogeneous in the sense that at every point locally they look the same. So imagine maybe a sphere, a plane, hyperbolic plane. They are examples of symmetric spaces, and their quotients would be locally symmetric spaces. I'll give you better definitions later, but now let's be informal. So you know, we have those kind of strong constraints on local geometry. So you can imagine like curvature tensor is very restricted. And we're asking how those local geometry constraints put constraints on the topology of the space. And we'll see some examples later how this happens. And we also want to understand how those local conditions force some relations between geometric invariants and topological invariants. And also we'll see some examples of this happening. So suddenly, normally, when you have no restrictions on Riemannian metric, there is a little of an interplay between geometry and topology. But when you force it to be somehow nice, there is lots of kind of back and forth. So yeah, let's talk about some examples. So one of the simplest examples of symmetric spaces are hyperbolic spaces. So hyperbolic n space is a complete contractible Riemannian manifold with a constant sectional curvatures equal to -1, and those conditions alone they determine it up to isometry. So there is a unique hyperbolic n space, and but to work with them we need some explicit models. So those hyperbolic n spaces admit many models, and each model comes with its own advantages and drawbacks. So I'll show you two models. So first is the upper half-plane model. So in this model, our space, hyperbolic space, is just the upper half-plane in some Rn. So you have n coordinates, and the last one has to be positive. And we define the Riemannian metric by this formula. So it's like it would be like Euclidean metric, but you scale by a factor xn squared. So so this is one way of defining a metric, and is with ds square equal this. So the way you can think about it is that if you want to compute the length of a curve, you would be integrating the sum of squares of derivatives of all coordinates of the curve divided by the square of the last coordinate, and take square root of that and integrate, and that's how we get the length of a curve in this space. And once you have a length of a curve, you determine the metric, like in ordinary sense. So in this space, the geodesics, which are locally length minimizing curves, are either vertical lines pointing up or semicircles hitting the edge of the space, which is just the part of the space where xn is equal to 0 at the right angle. Right, and I'm sure if you are into number theory, I'm sure you have seen lots of pictures of fundamental domains of some groups acting on hyperbolic plane, and they kind of have similar pieces to this picture. The second popular model is the Poincare disk model. And in this model, the space is the interior of the unit disk, and the metric is given by this formula. So it's like Euclidean metric, but as you approach the boundary, you scale it up by some enormous factor, right? This blows up to infinity. This denominator blows up to infinity as you approach the boundary. And geodesics are either vertical lines passing through the center, the 0, or half circles or semicircles meeting the boundary of the space at right angles. So I drew several here. Okay, so those spaces have constant curvature -1. And but those are kind of okay. They're contractible, so you can say they're boring from topological point of view, but they will have many finite volume or compact quotients, which are kind of arguably more interesting. So those are hyperbolic manifolds. So an n-dimensional Riemann manifold M is called hyperbolic if it has constant curvature -1. And this term, well, okay, now just to save time and space, we'll always talk about complete hyperbolic manifolds. So I'm not interested in manifolds where you throw away some points. And if M is hyperbolic, then the universal cover of M is isometric to Hn, to hyperbolic n space. And conversely, every manifold which is covered, Riemann manifold which is covered by Hn is hyperbolic. So if you want to understand hyperbolic manifolds, it's the same as understanding all quotients of Hn, right? And okay, yeah, right. Yeah. So already in surfaces, we can see a lot of kind of interplay between geometry and topology. So as you might know, closed surfaces, so compact two-dimensional manifolds. We'll assume everything is positively orientable. The surface is determined by genus, and genus is the number of holes in a donut, where you see the picture of a surface as a donut, and genus is number of holes. So the sphere has genus 0, ordinary torus has genus 1, and pretzel has genus 2. And we know that like genus already determines the surface up to homeomorphism. The Euler characteristic of a surface is kind of a function of the genus, 2 minus 2g, so it also determines the surface. And the link between geometry and topology is given by Gauss-Bonnet formula, which says that 2 pi times the characteristic of our surface is the same as the integral of the sectional curvature over the surface, and or Gauss curvature, and like in surfaces those are the same. So because we know that sectional curvature is everywhere -1, this integral is just minus the volume. So you see the relation between Euler characteristic and the volume, and therefore a volume alone allows you to completely determine the topology of the surface. So this is quite rare. Right. And that's the kind of simplest instance of this kind of dictionary between geometry and topology. Now we'll move to higher dimensions, where another interesting things happen. So we no longer have really Gauss-Bonnet, but we have different things. So there is a theorem by Wang, which says that for hyperbolic n manifolds, where n is at least 4, we actually only have finitely many manifolds of bounded volume. So there is some rigidity. For example, you cannot have a continuous families of hyperbolic for manifolds of finite volume, because then you would have uncountably many below given volume. This theorem says it's impossible. So there's some rigidity. You have only finitely many. This theorem is not true for 3, but it failed. Okay, the way it fails is not drastic, I would say. The number of, I think that, okay, let me maybe not comment on that, but in dimension 2, this theorem is completely not true, and we do have continuous families of surfaces below given volume. So this is kind of higher dimensional phenomenon. And in dimension 3 or higher, there is maybe even more surprising thing happening. It turns out that the fundamental group of the manifold, hyperbolic and manifold, already determines its isometric class. So kind of a weak, no, well, maybe not weak invariant, but pretty kind of purely topological invariant, like fundamental group, determines the whole geometry. So this is very, very kind of nice. This theorem kind of kickstarted a lot of research in rigidity theory. So I said the result for compact hyperbolic and manifolds is due to Mostow, and the non-compact version for finite volume manifolds is due to Prasad. So this theorem also fails for n equal 2, because every two surfaces of the same genus have isomorphic fundamental groups, but they don't have to be they don't have to have the same hyperbolic metric. Actually, the space of hyperbolic metrics you can put on a surface of genus G is like forms a manifold of dimension 6G minus 6. So in particular, it's uncountable.
Sorry, I have a question.
Yeah.
Maybe it's a stupid one, but you mentioned that from this theorem of Wang, it follows that there can't be uncountably many hyperbolic manifolds. And okay, I agree that this is a corollary of it, but still, is it somehow possible to prove it much easier, in an easier way, or?
No, I wouldn't say. I actually the number of manifolds below given volume is, as I see it, quite artificial quantity. So they don't obviously live in any common moduli space. So I wouldn't know how to approach it in any different way.
No,
The Wang,
I
yeah.
mean this corollary of this theorem, which states that there cannot be uncountably many of any volume. Yes, since that's how I understood your remark, that if you would have uncountably many of them, then you would have some accumulation point beneath some particular volume, and therefore this contradicts this theorem. So I wonder whether this corollary could be somehow proven in much easier way, since it.
I would bet that you still need to repeat most of Wang's argument, even to prove that just that corollary.
Okay, thank you.
Yeah. So yeah, next thing. So we talked about hyperbolic spaces. They have some rigidity phenomena, as we saw, but the real rigidity starts in higher rank. So we have to talk about other symmetric spaces for that, and I'll just briefly talk about them. But I cannot define for you too many because we don't have time. So hyperbolic spaces are just kind of the entry, kind of gateway drug to symmetric spaces. In general, there is a dictionary between symmetric spaces and semi-simple real Lie groups. And I'm ignoring several families of symmetric spaces that people study. I focus on something called symmetric spaces of a non-compact type. So they correspond to semi-simple real Lie groups which have no compact factors. Think about S ln R, for example. So for each symmetric space X, the isometry group is actually a non-compact semi-simple Lie group. And we can recover the space by dividing this group by one of its maximal compact subgroups. So all of those spaces are quotients G mod K, where G is semi-simple Lie group and K is the maximal compact subgroup. And I would say that the simplest example of symmetric space which is non-hyperbolic is just the product of H2 cross H2. This would correspond to the group SL2R cross SL2R in that dictionary. So the symmetric spaces have, are there any questions about this? I didn't know, did I move on? So the symmetric spaces have an important variant called the rank. And the rank of a symmetric space is the dimension of a maximal flat subspace, which is just an isometric copy of R to some power in X. Hyperbolic spaces have rank 1 because the only flat subspaces are the geodesics. And to get higher rank spaces, you can, for example, take the space which is the quotient of SL3R by SO3R. This is the space of, you can think of it as a space of positive definite 3x3 matrices. There is a natural metric on it, and yeah, this is like a rank 2 symmetric space. It has subspaces that are isometric to R2. You can also, well, there is another way to think about this space, that this is a moduli space of Euclidean metrics on R3.
Sorry, I now have previously I had stupid question, and now I have a very stupid question. You assume your space always to be non-compact, this X?
Yes.
Okay, but still, from the definition of a symmetric space, it does not follow that the space is non-compact. For example, a sphere is a symmetric space. Yes?
You're correct. Absolutely.
Okay, so you restrict your attention to symmetric spaces which are non-compact, yes?
Yeah.
Okay, thank you.
There is this subfamily which are called a non-compact type, and maybe to kind of the fastest way to understand this is that this is a space which has non-positive curvature. It's not flat, doesn't have flat factors, and I think that's enough. That's enough. Yeah. So I'm excluding spheres. I'm excluding Euclidean planes. I am excluding products with spheres and so on. There's kind of they behave differently, so it makes sense to kind of split the theory into non-compact type and the others. Right. So going back to higher rank spaces, the presence of those flat subspaces of dimension 2 or more, it makes them surprisingly more rigid than hyperbolic spaces. And I won't have time to talk about this rigidity more, but you can look up Margulis superrigidity. This is like a super nice theorem for which Margulis was awarded Fields Medal in 70s, which kind of says that like topology determines geometry in a very strong sense in those spaces. And locally symmetric spaces in general are spaces of the form X mod lambda, where X is the symmetric space and lambda is some discrete subgroup of the, I forgot to add this, a discrete subgroup of the isometry group of X. So denoted G on the previous slide. So you take discrete subgroup of G and you can quotient X by this discrete subgroup and you're getting some manifold or orbifold. Well, if we assume that group is torsion-free, then you get a manifold. So those, maybe one more comment, those higher rank symmetric spaces are spaces for which we expect many new phenomena that don't happen in rank 1. They kind of inherit some properties of R2. And this is, I cannot really go deeper into this, but they are kind of, in some ways, best behaved spaces if you look for rigidity. We are interested in those dictionaries between geometry and topology for those spaces. So the kind of questions I'm interested in and my collaborators are, for example, how large are the dimensions of homology groups of those higher rank local symmetric spaces with coefficients in some field. So this question was solved quite a long time ago when the field is characteristic 0, but it's still quite mysterious when the field is positive characteristic. A related question is how many torsion elements you have in homology groups or cohomology groups. And you can also ask what's the minimal number of generators, we call it the rank of the fundamental group of the manifold. So those are some kind of topological invariants that control the complexity of the manifold. And it turns out that all of them can be reasonably controlled in terms of the volume of M. In higher rank, right? In rank 1, sometimes not. And in those questions, we will assume that M is a finite volume locally symmetric space or even a compact one. Okay. So I will focus maybe on this third question. It's harder than question number 1 in many aspects because this fundamental group is a non-abelian invariant. It's kind of harder to control. You have no Hodge theory to get easy access to it. So it's going to be quite difficult to estimate the rank of this group. So we have, nevertheless, we proved one result about the growth of this rank. So this is a special case of our theorem. This joint work with Sam Melick and Amanda Wilkins that we posted on arXiv in 23, and now it's in review. So we start with a simple higher rank symmetric space. So you can maybe forget about the adjective simple. For example, the space coming from SL3 or SLN will work for any n bigger or equal 3. And we have a local symmetric space M just has finite volume or even is compact and it's covered by X. So this is a quotient of X by some co-compact subgroup of isometries. And we would like to understand how does the rank of the fundamental group grow when we increase the cover. Oh, well, this lambda, this gamma should have been pi1 of m prime. Sorry. So we want to understand how the number of generators of the fundamental group of the cover grows in terms of the degree of the cover. So you can have some elementary arguments which say that this number of generators grows at most as fast as the degree. So it's like some constant times the degree. But it's actually quite difficult to show that you can do better.
What is the degree of the cover?
You have each point has, it's the number of points in the preimage of each point.
Okay.
Of a map. Right, so you can also understand it as ratio of volumes. Anyways, yeah.
Okay.
Right, so we in the paper we actually proved that this number of generators, which we call the rank, is sublinear in the volume of the manifold. But there are some technical conditions in that case, so I wanted to avoid that. So maybe one comment that this is not true for surfaces. For example, when you have a surface of genus G, then it's the genus of a cover grows kind of linearly in the degree of the cover, and at the same time, the rank of the fundamental group is 2G. So we see that for surfaces, the rank of the fundamental group is actually linear in volume, and therefore it would be linear in the degree of the cover. So there you couldn't show small o. You need high rank for this. Well, the question about hyperbolic spaces of dimension 3 or higher is still open, and I think it's the hardest question one of the hardest questions in this theory. Right. So I would like to say a few words about how we approach this, how we prove this result. So how we prove that you can find small number of generators for fundamental groups of some manifolds. And it shouldn't be surprised that I will want to use probabilistic method, because that was the title of my talk. So we'll try to cook up some probabilistic models that will produce a small generating set for us. And how do we do that? So, well, generating sets are kind of algebraic, and for this problem we expect that we'll use geometry, so we would like to think more geometrically. So instead of trying to find generators in the fundamental group, we'll try to draw some graphs on the manifold. So we'll construct some random graph in the manifold. Let's call it G, and imagine that this is like a graph drawn on the manifold. There will be a picture on the next slide. And we would like to show that this graph pi1 surjects, meaning that the fundamental group of the graph surjects onto the fundamental group M. So this means that every kind of loop in M could be homotoped onto the graph, right? So it's kind of captures all the elements of the fundamental group. And then we could simply bound the number of generators of pi1 of M by the number of generators of pi1 of G. The fundamental group of a graph is always a free group, and you can compute its rank in terms of the Euler characteristic of the graph, which is number of vertices minus number of edges. And the rank of a pi1 of a graph is always 1 minus the Euler characteristic of the graph. So the estimating of the rank of the fundamental group of a manifold can be reduced to estimates on the Euler characteristic of those random pi1 surjective graphs. So now let's consider a simple example. It will be an example of a torus and its covers. Using probabilistic method is of course an overkill in that case, because the generating sets are quite obvious, but nevertheless, let's try to do it. So this is a ordinary torus, a donut. And here I have drawn in blue a graph on this torus that surjects onto the fundamental group. So you see that, like in the torus, fundamental group is Z2, And we have two generators of the Z2, which are loops corresponding to those two blue circles. And we see that, you can find generators of the fundamental group as represented by loops in the graph. So pi1 of the graph will surject onto pi1 of the manifold. And note that this is surjection, not isomorphism, because pi1 of the graph will be a free group on two generators, while pi1 of the manifold will be Z2. Okay, so now let's draw a more pleasant picture to work with. So we unravel the torus. This is a square with opposite sides glued to each other, and in those coordinates, this graph looks like this. If you now want to understand how the rank grows when you take higher and higher covers, well, you could try to draw those graphs on covers, and we know that we could just draw the same graph on a high cover, but let's pretend we don't know that. So what we could do is just lift the graph to the cover. So if you have some high cover of the torus, if you lift this graph, you get some kind of a grid. This doesn't really give us a good bound because the Euler characteristic of this grid will grow linearly in the degree of the cover. You see that we use kind of way too many edges. We don't need all of them to generate the fundamental group. So we could, okay, this is an example of something that doesn't really work, but we could be a little smarter and, for example, try to kind of first pick a sparse subset of points in a torus, assign some kind of cells to each of them in such a way that you tessellate the torus. Like in this picture, those red cells are assigned to every point. Later, I'll tell you how you can choose those cells nicely using geometry. And then when you have this nice tessellation, you can consider a dual graph where vertices correspond to cells and two vertices are connected if and only if the cells touch. And there are some easy conditions you can check about the tessellation that will guarantee that this graph is actually pi1 surjective. And if you draw big cells, then the number of points that you'll use, the number of edges that you'll use will be quite small compared to the degree of the cover. And you will find some kind of a graph with small Euler characteristic compared to the degree of the cover. And we will be done. We will complete this sketch that I explained to you. Okay, and as you see, for a torus, this is a way overkill because you could just repeat the same picture on the cover. Yes?
So somehow I didn't get it, how to construct this random graph. So what is random in your construction?
Oh, here there is no randomness yet. I mean, you could make it random by choosing those points, 4 points at random, and then construct the tessellation. But you can imagine you get somehow this picture randomly.
Yes, but how about edges?
Sorry?
How about edges? Edges between
edges will be a function of the points. So once you select the points randomly, the edges are kind of determined by the tessellation. So in a moment, I'll tell you how you can construct this tessellation. This will be called Voronoi tessellation. Maybe some of you know it. So in next slide, I'll actually explain how you want to do this in higher rank, because it's in some sense it's similar to this picture in the torus. Okay, so what do we do? Imagine this picture is our piece of our manifold. Of course, you cannot really draw higher rank locally symmetric spaces on a blackboard. Lowest dimensional one is 4-dimensional, and lowest dimensional simple locally symmetric space is 5-dimensional. So it's hard to draw it. But what do? We have a manifold, and we want to first select a sparse random collection of points on the manifold. So we pick some small epsilon, and we choose epsilon times the volume of M independent random points in M. So, each point is just random point in the manifold. The notion of volume allows us to talk about randomness, right? It's random with respect to the volume measure. And this set has a small number of points compared to the volume. And the volume, let's just forget about degree of the cover and think about volume, because volume will be comparable to the degree of the cover. So we call this set S. Those will be vertices in some sense of our graph. And now we consider the Voronoi tessellation given by this set of points. So Voronoi tessellation is like a way of dividing Riemann manifolds into cells, where a cell corresponding to a point S, denoted CS, consists of the points of the manifold which are closer to this point than any other point in the set. Okay, so this is called Voronoi tessellation. And here I tried to draw a picture how it would look like if our manifold was just two-dimensional flat manifold. Right, so we're trying to for each point we're looking for the closest one in S, and this is this, then it belongs to the cell of this point. Okay. So this is what I would actually do here. So I would pick some sparse family of points in the torus and draw Voronoi tessellation, and they then take this dual graph. Okay. And we can do this in higher rank symmetric space too. So then we would be taking this dual graph to this tessellation. So so vertices are kind of our cells, which we can visualize as the centers of the cells. And we're dividing two cells if they share a common wall. So here, as in the picture, the points are divided if their cells touch. And this is dual graph of tessellation. So maybe a word of warning that in higher rank, actually, you don't know that the walls, the intersections of two cells are actually connected. So it's not as easy as in this picture, but you can nevertheless do this. And then the only random thing here was the choice of points, right? Everything else is deterministic in points. And then it turns out that you can, in a way, compute the expected Euler characteristic of this graph. This Euler characteristic is given by sum over all points in our set of 1 minus degree of the point is in this dual graph over 2. And you can understand it like this. Euler characteristic is the number of vertices minus number of edges. So here we put 1 for every vertex, and every edge is counted twice, so we subtract degree over 2. It turns out that using high rank geometry, you can kind of understand this quantity, this degree of a point. It turns out that in higher rank, those cells that you get by looking at Voronoi tessellations, they tend to have long walls, and therefore their number of neighbors is actually small compared to the volume of the cell. So this is where we use higher rank. By the way, what I'm talking about here is kind of an idea of the proof. In the proof, we have to do this in a more technical way, which will be completely unexplainable. But kind of the geometric idea is here. The cells have small number of walls compared to their volume. Therefore, when you look at this formula defining Euler characteristic one more time, this one, versus the formula for the volume, which could be recovered as the sum of all volumes of the cells, you're comparing sum of small o's versus of volumes versus sum of volumes. And you can actually prove that this whole sum, which gives you Euler characteristic, is a small o of the volume. So you constructed a graph which is pi1 surjective. Its Euler characteristic is small o of volume, and that means that you can find a generating set which is small o of the volume. That's how we proved it. Yeah, this doesn't work for rank 1. The cells in Voronoi tessellation in rank 1, they have very tiny walls of kind of constant size. But in higher rank, you can show with good probability that they have long walls. And that's why the argument works. And it's, I think so far, there is no non-probabilistic proof of those bounds, maybe except some special cases. Okay, so let me finish by 1 minute by mentioning other applications of probabilistic methods in topology and geometry. So there is a lot of exciting work about random finite covers of hyperbolic surfaces. In some sense, they're very good expanders. In the same way, random graphs are very good expanders. And there is a recent breakthrough by Hyde-McGee, who constructed like almost Ramanujan surfaces in this way. There's also older work by Karl Markovich where they use a blend of probabilistic and dynamical methods. Maybe not everybody would agree that they're probabilistic, but I see them like this. To find interesting submanifolds of certain hyperbolic free manifolds. And those works were extended to other symmetric spaces, local symmetric spaces. And finally, there is my own work with Jagiellonian where we use kind of blend of probabilistic and dynamical methods by considering certain random walks to study infinite volume local symmetric spaces and prove some interesting things about infinite covolume higher rank symmetric spaces. And this thing goes through the notion of random discrete subgroups, which is kind of grew to its own area of math by this point. Okay, and I think that's everything I wanted to say. So thank you for your attention.
Thank you for the lecture. It's absolutely perfect timing. Well, are there any questions? Please.
I have a question about the expander example you gave at the beginning. So you mentioned that quite often a probabilistic proof can yield a probabilistic algorithm. So does that happen here?
No. I don't think so, because verifying that something is expander, I think is actually hard. Because the probabilistic proof gives you a probabilistic algorithm when you have a quick method of verifying that the thing you found works. But for expander graph, I'm not aware. Maybe there are experts who know more. I'm not aware of any quick algorithms that would verify that the graph is an expander.
Okay.
That's why in that particular case, if you want to be sure, you have to use explicit constructions. But maybe I'll add that the way if random graph fails to be an expander, this failure is not catastrophical. So what would happen is that you would have a big chunk that is an expander and some small parts which fail, but they are small. So if you care about robust networks, you can accept small number of nodes where things don't work.
Thank you.
Okay, are there any other questions or comments, please?
Are you familiar with some example which involve this probabilistic methods, graph theory, and also the so-called notion of Gromov-Hausdorff distance, where you would have something like, I don't know, something combinatorial, but the sequence of some objects which are combinatorial in some sense converging to something which is smooth, and in this case that you can somehow extract those using this probabilistic method, extract something from a combinatorial world to this continuous world of manifolds.
So you like manifold bound? Okay. There might be some work by Lipnowski and Friend and a collaborator, maybe Lin. Sorry, I'm not sure. Okay, Mike Lipnowski did some work where he studied some spectral questions on manifolds by considering fine triangulations on those manifolds.
Could you please repeat the name?
Mike Lipnowski. I'll write it in the chat. I cannot. I can.
Or maybe you could spell it since. Okay, Mike Lipnowski.
You can see it, yes.
You can see it?
Yes, we can.
Yes, we can see.
So yeah, but I'm not sure he goes to the limit. In my experience, if you try to, like, okay, you have some random model of graphs and you want it to converge to the plane, and you want some interesting things to happen, you can quickly venture into very difficult parts of math which are related to Liouville quantum gravity, and have many technical problems which those people love. But I'm not sure. I'm not sure this would be an ideal tool to study a manifold.
Okay,
Yeah.
but you mentioned some connection with this Liouville quantum gravity, which is a topic of independent interest, yes?
Yeah, it is.
Okay.
Like, yeah, if you try to approximate continuous space-based graphs, but you kind of want to make the approximation random, then you can get this. This is somehow related to Liouville quantum gravity, but I'm of course I know next to nothing about this. Your question, initial question, if you kind of accept different limits than manifolds, like there are kind of theories when you can take graph limits, then answer would be yes. You can use probabilistic method to construct sequences of graphs that converge to interesting probabilistic objects with some properties.
Oh, okay. So not
Right,
necessarily
but I'm not aware.
manifolds, but it's still something interesting, yes?
Yeah.
Okay.
For example, this work of Hyde-McGee, what they do, they want to construct hyperbolic surfaces which have a spectral gap almost 1/4, which is the kind of the optimal if you have large one. And some deep conjectures number theory, they predict that you should have many examples, but nobody was able to verify that. And they found that a high degree random cover of any given surface has spectral gap almost 1/4, which is almost optimal. And I think this is an annals paper now.
Okay, thank you.
Okay. Are there any other questions or comments? And from people on Zoom? Okay, if not, let's thank Mikołaj again.
Thank you.
Okay, and I will stop recording. No, this was the name of Lipowski.